Okay, I'm here to finish up, I hope, talking about single mode optical fibers. And what I want to do is I want to put this single mode fiber slide up, the one from the last video, and note that so far I've talked about the SMF28 varieties, I've talked about the clear curve single mode, but I haven't talked yet about leaf or vascade fibers. So I'll do that now. And so we've got single mode fibers, leaf, and the vascade varieties. I've almost made these slides entirely so it goes quicker. But in order to understand the leaf and the vascade fibers, we have to understand two concepts first. And we could have an entire chapter in the book on these topics, and in fact there are a number of books out there that do a more complete job of covering these subjects than Peleus does. I don't think Peleus treats the nonlinearities really the way I'd like to see it done. So the first concept is dispersion shifted fibers. Okay, so let's look at dispersion shifted fibers. Here is a picture, sort of a schematic of the index profile for a step index fiber. It's index N2 in the cladding, and then pops up to index N1 in the core, and then back out to N2, where I'm plotting versus the radial. So it's symmetric about r equals 0. Okay, I really only need to plot half of this, but I'm plotting the whole thing here. So what happens is then in the step index fiber we do get a waveguide contribution to the total dispersion. So we have our material dispersion shown here in black. Okay, it has this zero dispersion point at about 1300, and then we have the waveguide dispersion shown in blue, which is much smaller, and it has the same size, the same sign as material at less than 1300 nanometers, and it actually has the opposite sign as the material dispersion at greater than 1300 nanometers. In any case, the total material dispersion is the sum of the two. And you can see what it's done is it's shifted the zero dispersion point. Adding the waveguide dispersion into the material has shifted the zero dispersion point slightly above 1300. It turns out you can vary the index profile according to various different schemes and different profiles to cause the waveguide dispersion to be much larger. So if the waveguide dispersion were in fact increasing, you know, something like, oops, I guess I'm doing waveguide in blue, something like this, then you can see that we can move the zero dispersion point of the fiber, the total dispersion, all the way out to 1550 nanometers. And that's exactly what they do with dispersion shifted fiber. Okay, so this is dispersion shifted fiber. So this is dispersion shifted fiber, DSF. Okay, and what we've done is we've shifted the 0 point out to 1550 nanometers. And what that means is that when we run at 1550 nanometers, we have essentially zero dispersion. And that's great because our bandwidth distance product is fantastic then, especially if we're working with just a single wavelength. Even if you're working with a WDM system with the wavelengths in the range of 1530 to 1570, you have quite low dispersion in that range, and that really increases your bandwidth distance product. Okay? So by engineering the index profile of the fiber, you can create what's called dispersion shifted fiber, which is optimized with very low dispersion, sometimes positive, sometimes negative, out in the 1550 range. Okay? So that's the first important concept about dispersion shifted fibers. And I'll go on to the next two slides in the next videos. So thank you.